caught one of my presentations before in the past, or if this is your first time here tonight, I can see a couple of blue dots in the audience. Thanks very much for coming along. My name's Rob. I normally go by Bok pretty much everywhere. That's my handle on Slack, on Mastodon, and that's what they call me at work too, so, you know. I am one of the organisers here, but I'm actually, my day job is an iOS engineer over at ANZ. So as a bit of a background, if you haven't seen it yet, I actually gave a presentation on ANZ Plus, the app we've been building for the last 3 years. I feel weird saying 3 years, it really doesn't feel like 3 years. I think it was May last year, so 12 months ago, up here on this stage. And at the end of this session, if you haven't seen that one, I recommend going back and watching that. It's on the CocoaHeads YouTube channel, and it's a really good insight to what we've built. So tonight, to continue the HTTP theme, I'm going to talk a little bit more about the underpinnings of the ANZ Plus app and how we build and manage the APIs themselves that drive it. So we're all familiar with this one, right? We should know what a HTTP request looks like for the most part. It has a bunch of headers that we send as part of a request, has a request body. It could be a JSON payload, it could be, happens to be an XML payload, could be some other stuff, but it's a request and a response that has headers, that has a body. So let's add some structure to that. Right, we're going to use this quite a bit, so we'll try to keep the colors good. Hopefully there's nobody red-green colorblind in the audience. If so, I'm sorry, did not think that through. But the request we send is made up of HTTP headers and has a body. And the response is similarly made up of headers and a body. So I'm going to do some very poor attempts at being an enterprise architect here and put them into some sequence diagrams. So on the left-hand side, we've got the client. The right-hand side, you've got a server of some sort. And there's some messages going back and forth, right? I can see the only architect in the room shaking his head, so this is going well. The headers are obviously set before the message body as well. And then the response goes back the other way. Nice and easy. This is what we know as HTTP 1.1. So Simon covered that quite a bit already in his, with the request and the response types. And this was, yeah, HTTP 1.1. It's been around for 30, 40 years, probably 40 years, I think. But it's not best practice anymore. There's a new one, HTTP 2. I'm going to kind of evolve on this a little bit. So it's more or less the same thing. HTTP 2 is just a request and a response going back, right? But for one, in HTTP 2 we generalize things a little bit more. And it's basically a series of what they call frames going from back and forth between the two participants. And the frames have different types. They simplify the terminology down a little bit because it doesn't really matter if it's going this way or if it's going this way. It's still a frame that has some headers and it's still a frame that has some data. So we'll just label it like that going through this. So we'll dive a little bit deeper into HTTP 2. They refer to each connection as a stream. Stream is actually one level above the connection, and I'll explain that. But a stream is a sequence of frames that goes back and forth between the two participants. So there can be multiple streams running in a HTTP 2 connection. That was one of the downsides of HTTP 1.1. It required a lot more actual connections between the two servers, whereas HTTP 2, so if you were to connect to google.com, in HTTP 1.1, they would do a new connection potentially for every asset you downloaded, so every style sheet, every image, every JavaScript file. But in HTTP 2, it will reuse the one HTTP connection and just open a different stream and multiplex the streams inside that connection. So because HTTP 2 is just a sequence of frames going back and forth between two participants, we're not actually limited to a single header frame and a single data frame. We can send as many data frames as we want, really, right? And you can take this as far or as long as you want. You can leave your HTTP stream open for up to as long as your network hardware will allow and send as much data back and forth going in each direction. So whereas in HTTP 1 world, we had to build things like WebSockets that Simon was talking about to get around this limitations of HTTP 1.1. HTTP2 has all of that built in. There's no need for separate things. And the way that it terminates, just to complete the loop, is you slap a end stream marker on one of the frames to let the remote end know that the stream is finished, pretty much. And that will cause the HTTP2 implementations to close the stream, but not the connection. The connection stays open for the next stream that comes through, unless you choose to close it. So that's lovely for happy path flows, but what happens if something goes wrong on there? Well, it's not just multiple data frames. You can also send a headers frame at the end of the stream as well to provide on, well, some additional HTTP status, any metadata that you want to send, but it calls them trailers this time instead of headers. And one final note here before we move on. This is my only lecture on HTTP, I promise. One final note is that they don't have to go all in sequence. They can talk back and forth as much as you want. The only rule there is that there must be a headers at the beginning, and then you can pretty much do anything you like. All right. So now let's build on top of HTTP2, and we'll talk about gRPC. gRPC is the alternative to REST as a API paradigm that we are using for ANZ Plus. Now, it was originally a Google concept and a Google tool that they built out, but thank goodness it has graduated from Google. It means they can't abandonware it anymore like they did with Google Reader. I'm not hurt, I promise. And now it's supported by a number of open source, or it's an open source project that's supported by a number of companies, including people like Apple. Apple has built stuff on top of gRPC. They support the Swift versions of this toolchain. But it builds on a very old enterprise concept of a remote procedure call, which is basically just a function running in a remote environment instead of on your local CPU. And in a way, Swift's distributed actors proposal is a evolution of this concept. Doesn't matter where your code's running, it's running somewhere, and you'll get a result back. So gRPC includes 4 different types of remote procedure calls. They have a unary request and response type, and then 3 different types of streaming that build on top of the HTTP2 capabilities we talked before. The first of these is a unary one, which is your basic REST style request and response. They call it unary because it involves a single data frame in either direction. And gRPC is intended to be protocol agnostic and language agnostic, so it differs slightly from HTTP2. There are other ways to use gRPC, including with JSON if you wanted to do that. But in gRPC terms, a data frame is known as a message, and the headers frame is known as a metadata. So I'll refer to that going forward. So for a unary call, the client will send the metadata headers and its message body, responds with its own metadata headers, a message body, and then the trailing metadata at the end. If we were to write this in Swift, it looks pretty much like what Simon had on his slides before, because it is basically a REST call, right? HTTP call. Method, async method, or throwing async method, takes a request type, returns a response type. The server streaming one, or second type that I listed on there, the client sends the metadata headers and your message body, same as your unary call, but the server then responds with one or more message bodies back, whatever it wants to do over time. And when it's finished, it sends the trailing metadata, and the stream marker to close the stream ends the call. In Swift, this would be the same as, instead of having the async method, it returns an async stream that will emit values over time. Basically how it works. No surprise then that the inverse of that is the client streaming one, which the client's the one that can send through all of the message bodies that it wants to, closes it off with the trailing metadata, and then the server will respond with its own headers, its own message response back, and then the trailers to close the connection. As with the Swift there, and I just realized that's a bit cut off. Yay, go Pat. The Swift there is just the async sequence goes in the other direction, right? It's not too difficult, and then the server will respond asynchronously as it goes. So the final piece then is a bidirectional gRPC stream. As the name suggests, it's just a stream that goes both directions, and it can send as many message bodies as it wants, very much the same as a function that accepts async sequence and returns an async sequence. Cool. Cool. So here's a practical example of how that works. Back in May last year, when I did the offline data talk about how we do offline data at ANZ, I showed this slide. And it shows the app connecting to a remote command center instance in the cloud. And then it ingests commands into the local queue before running them and synchronizing data as instructed. So what I mentioned at the time but didn't really have much time to elaborate on is that this is just a gRPC server stream. Right, so we connect to the server, it just sends us back a bunch of stuff. So if we were to represent that on my terrible sequence diagrams, I'm sorry, Matt, it would look something like this. The ANZ app connects to the command center with a HTTP2 connection. It calls the get commands RPC. The message body that we send to command center is a marker, a stream marker, so it knows where to pick up and where it left off. And then it sends us back the headers, the initial metadata headers, any messages that it needs to send us, so any commands that are waiting to be processed, and includes in a marker with every one of those commands that we will save as we process things. And then eventually it closes off, right? So the marker that we save is obviously the one that we will use the next time we connect. So that way we can pick up exactly where we left off the previous time. And if something goes wrong, say we get disconnected or that sort of stuff, we know we can pick up exactly where we left off and nothing is left behind. So for one more example of that, which I didn't get into last time, we want to talk about how we get transactions onto the device. Like Command Center, the transaction stuff is a gRPC stream. Unlike Command Center, it's a bidirectional gRPC stream. So we make a HTTP connection to the transaction service, and we call the RPC to get the transactions. We send a device ID so that it knows who we are. And in response, the transaction service will start sending us back any transactions that we don't know about. And each of those transactions will have a unique identifier that we can then use to acknowledge that we've received them. So because it's a bidirectional gRPC stream, we can send data in both directions. So we'll get a transaction, we acknowledge we've received that transaction, we've saved it to our cache. Everyone's happy, mostly happy. And this obviously goes on as long as it needs to go on. But if for any reason we're unable to send that acknowledgement back, so if we get disconnected, app crashes, doesn't happen, but if the app crashes, then the next time we connect, the transaction service would resend everything that we didn't acknowledge previously. So it works as a incremental sync of sorts. And then at some point we get disconnected. Right, so far I've spoken about the gRPC, which is the alternative to REST that we use, but I haven't really spoken about what goes inside those message bodies. It's not JSON. I put this slide in here purely so I can tap this button and use the next transition. I don't get to do this very often, but it's always very satisfying when I do. So here we go. Yay! So instead of JSON, gRPC is built on top of a format known as protocol buffers. Now, like JSON, it is intended to be language and platform neutral. Doesn't really matter what it's. JSON wasn't intended that way, it just kind of became that way in the end. It's also a serialized data structure like JSON, so we can send structures back and forth. But that's where the similarities end. It's a binary wire format, which means that it's sending binary data over the HTTP connections. It's not sending ASCII text or UTF-8 text if you can do it properly. So it's not designed to be human readable. JSON's designed to be human readable. But the benefits of that is, when you take a JSON payload and you gzip it down, the same payload in protocol buffers will be 84% smaller than the gzip JSON. So it has a lot of efficiencies in terms of network traffic and that sort of stuff. And this is then the most annoying bit of protocol buffers, but it's also the best bit of protocol buffers if you use it right. It requires a schema to be shared up front. It's not like a JSON payload where you can look at the payload and figure it out how you do it. You need to have the schema up front. If you don't have the schema up front, you can't encode messages in protocol buffers and you can't decode messages in protocol buffers. Well, you can, but you're going to end up in a lot more pain than not. Yeah. So one last thing, the Swift protobuf framework that we use for protocol buffers is written by Apple. It's built by Apple. It's maintained by Apple. It's an open source project, the same as Swift syntax or Swift format or any of the other Apple open source Swift initiatives. So this has got the backing of Apple, at least to that extent. All right. Did I miss a slide there? No, cool. So this is an example of a protobuf message type. So as a serialized format for sending messages back and forth, they prefix everything with message instead of struct, but it's pretty much the same thing. So if you were to try and describe a bank account, for example, I know a bank talking about bank examples, that's easy, but it's good. It's familiar, I guess is the word I'm looking for there. So if you were to describe a bank account, it might have three properties, the BSB account number and account name. They're all strings, as you can see from that, and they're assigned to fields 1, 2, and 3 in the protobuf message payload. Not going to go too much more into the depths of protobuf. We had to talk about this earlier today at the office, and it goes into a lot more detail. We don't have time for that today. That would be another 40 minutes on top of this, and we have to give the office back the space back at some point. But the field numbers in general are used for serializing and deserializing within the format, and they're very good for forwards and backwards compatibility, how it does that. But we can describe more than just the message types in protobuf. We can also describe the gRPC APIs themselves in there. So here's a basic bank accounts service that has a single RPC defined in it. It's a unary gRPC call, so that lists available bank accounts. You send it a message with the type of accounts you would like to filter for, and it will return a list of the matching accounts. Pretty straightforward. If you look at the declaration of that, it's actually pretty similar to the Swift code that we had up before. So it's very nice and easy for us. The repeated keyword in the list itself is basically how protobuf describes arrays as a shorthand. Now, so this describes a unary gRPC call, but what if we wanted to return a stream instead? It's literally a one-liner, the same as we would switch from the return type from the type to an async sequence. You just type in the stream keyword, and it will take care of the rest for you. If you wanted to be a client streaming one, you put the stream keyword in front of the request type, and if you want to be bidirectional, 2 stream keywords. So it's pretty easy. But did you notice something similar while we're looking at the protobuf? It's just code. It's just a different language from what we do, but it's just code. And as developers, what do we do with code normally? If we're doing it right, we throw it in source control. And if you have an API definition in code lives in source control, you have an API contract. Whoa. So here is how we manage APIs at ANZ. Protobuf definitions for all our APIs live inside a Git repo. We're all very familiar with Git, or the other alternatives that my name has escaped me now. Hopefully nobody's using Subversion here still, right? We're all on Git. We have agreed standards for the types and language features that we'll use. So as an example, we have an agreed way of how we do dates, which is one of the biggest contentions with JSON. Is it going to come back as a ISO 8601 string? Is it going to come back as a Unix timestamp? Spec doesn't say. You can do what they want, and often people will do what they want. I've seen some very weird date formats and calendar representations over the years. That doesn't happen because we have a type that is specific for this sort of stuff. We also have agreed ways we do API lifecycles. So no more sudden breaking changes. We have a agreed way of how breaking changes are handled, how versioning is done, how deprecations are communicated and managed, all of that sort of stuff. And APIs are considered to be a shared resource. This is not some generated Swagger or handwritten documentation that gets thrown into a wiki or a Confluence site and then left there to rot because nobody bothered to update it or even knew it was there to update it, more often than not. It's a living, breathing bit of code that engineers and developers can read, reason about, talk about, and iterate on, most importantly. So, because it lives in source control, API changes, then it's just a PR. Anyone can raise a PR. Doesn't necessarily mean it's going to get approved, but you can raise a PR and start a discussion based on that. It doesn't just have to be the people that maintain the backends that raise the PR to start a new API version. Anybody can do that. And we're all used to leaving feedback and collaborating on PRs by now. We all do it. Backend engineers do it as well. So why wouldn't you do that with your API definitions? It's all very, very nice and easy, very familiar. And the final piece of the puzzle then is there are required checks on those PRs to make sure that the SDKs for those APIs can be built in all languages that are supported. So for that final piece then, in the home stretch here, let's talk about how we get those protobuf definitions into Xcode. And that's pretty easy. It's just done, like it's one code in one language, and you want code in another language, so we just transfer it from one language to another. Or more accurately, we use the Swift protobuf package provided by Apple and the gRPC folks to parse the protobuf files, and then they spit out some Swift code at the other end. And that has a whole lot of benefits that you don't really see until you actually start using this, right? For the first part, it means you're not writing codable conformances anymore. Whether you use the synthesized codable conformances or whether you're using manually done codable conformances, there's no more copy-pasting JSON properties from your JSON payload into Xcode to make sure you don't accidentally typo a property name. There's no more codable conformances. It means you don't have to spend energy writing tests, unit tests, to make sure that your JSON coming from the server passes. It's not a thing you have to do. And then there's no more time keeping those unit tests up to date as your APIs evolve over the years. And it's not just Swift. Like, this is very much a Swift-focused talk, but it's not just Swift that's generated as well. You can generate Kotlin libraries from the protobuf. You can generate frameworks for Go, for Python, for Ruby, JavaScript, if that's your thing. Whatever you need, you can generate it from the protobuf. So that means as long as you and the people writing your backends are generating SDKs from the same protobuf definitions, that you're guaranteed that the protobuf messages that are encoded or created by the backend are passable by your front end. You don't have to write the tests anymore to confirm that. And most importantly, it means there's no more fragile JSON payloads. How often have your apps broken because the backend team accidentally started returning a double or a string instead of an integer? It can be quite common, especially if they're working in Node or something else that's not a type-safe language. Their IDE is not going to yell at them if they suddenly start returning the wrong type into what is effectively a dictionary with any as the thing, right? But the generated protobuf SDK, the types that are generated by protobuf, the code generation, are strongly typed. So you will start to get an error if you're sending the wrong thing through. So if they do that, it means that the backend code just doesn't compile anymore, and they have to fix the error before they can move on. So what does the generated code look like? More or less exactly like you would expect. It generates a struct that conforms to the message type. It has 3 properties inside there that all look like strings. The Swift protobuf message protocol is what handles all of the decoding. And there's a little bit of boilerplate that I've left off this slide because it would then get quite big and quite unreadable, but it's all just generated for you by the SDK. You don't have to think about any of that. the generated gRPC clients themselves are the same. It generates a protocol and a client implementation for you, and we should all be able to, that should all look pretty familiar to us. The bank account service has a single method, same method that exactly the same name that was in the protobuf code, that accepts a bank account's filler type, which would be a struct, and returns a unary call handler that is specialized with the expected request and response types. You can see that it generates the bank accounts list response type as well, and the repeated list of accounts has been transformed into an array. It's all pretty clean. As for actually using that code, that's pretty straightforward too. You create a client connection, which is built on top of Swift NIO. So again, another common theme with Simon's talk from before. Everything seems to be built on top of Swift NIO these days, so yeah. So gRPC will call this a channel, again, because it's protocol agnostic as far as that goes. So once you've created that channel, you create your bank accounts client, which was the generated SDK code. You pass in the channel so it knows how to do the communications back and forth. And then you just use async await on the contents like you normally would. You can also wrap it up into a combined publisher if you're not at the async await adoption stage yet. Otherwise, there is also completion handlers that you can use as well. So, yeah, pretty straightforward. But the important thing here is that all of the communication, decoding, encoding, serialization, deserialization, what do you want to call that? That's all done by the generated SDK code, not code that you have to take responsibility for and test. It's just all generated. It's lovely. So how do we generate those? And this is the last little bit. How do you generate them? How do you get them into Xcode? You use CI, like your GitHub, your Jenkins, sorry if you're using Jenkins, your build kites, any of the CI platforms that are readily available. It's just code that you're running at the end of the day. So this is the last part, and I promise it's worth it to see just how much of an impact this has on your code base. So we'll get there very quickly, I promise. But as a little bit of a side note, if you were here last month to see Marcelo's talk on using VS Code for Swift, this is actually what he's built with using VS Code. So there's no Xcode involved in any of this little bit. It's all Swift, which is lovely. So the process of raising an API request starts as you would imagine. You raise a PR, that PR is reviewed, CI checks run to make sure that everything can generate successfully, they haven't done anything illegal, and then it gets approved, and then it gets merged. From there, we tag a new version of the API, kick off a workflow to generate the Swift code using Apple's Swift protobuf framework, and the gRPC generation tools as well. We wrap that up into a binary XC framework. This is usually the heavy compilation step because it involves compiling Swift NIO, and nobody likes that. But CI does that, and not you on your Mac. And then we throw that up into a registry somewhere. But really, it boils down to this. You raise the PR, get it approved, the binary target's uploaded somewhere, or the XC framework's uploaded somewhere. You add a binary target to your package.swift file with the name, the URL, and the hash, the SHA for that package. And that's it. Xcode will download that, manage that for you, gives you just like any other Swift code that was compiled locally. It's very cool. In the future, when we get to Swift package registry support, this will be even easier. You won't need to look up the URL and the SHA anymore. It will just be, pass the package name and the version number into Xcode, and Xcode, Swift PM will do the rest. Swift PM is not quite there on this one yet, but we're getting there. And that's it, right? So just to recap, you want a new API version, you raise a PR, get your PR approved and merged, you bump your version number in Xcode. That's all that's involved. There shouldn't be any more than that. There's no going in and updating your codable definitions, no going in updating your codable unit tests. It's just done. If there are any changes to your generated code that Xcode doesn't like, it will throw a compiler warning. You go and fix those compiler warnings, and then you're guaranteed to have something that will be able to talk to the server without errors. Compiler guarantees that, instead of unit tests, which is very nice. But if typos are the bane of JSON APIs, where in this process can humans make a mistake and typo something and make it go wrong? Well, there's really two places. If you make a typo in your protobuf definition, doesn't matter. It will be frustrating and annoying that all of your generated SDKs have a typo in them, but everything will compile, everything will serialize and deserialize, doesn't matter. And if you type the package ID or the version number wrong, Xcode will just say no. And that's why I went with the clickbaity title at the start that says Unbreakable APIs for this talk. It's pretty damn hard once that's all set up and working to get this wrong. But hey, Xcode will always find a way at the end of the day. And that's it. That's everything I've got. I'm happy to take questions now. I've written up a couple of answers to questions I expected because I didn't want to spend another 10 minutes talking about this. But yeah, if anybody has any questions, please feel free.
Anyone? The big nasty one, versioning.
Yep. Versioning, yeah, which I didn't talk to here. So we include the version details in the package name. So it becomes a separate package, basically. For forward and backwards compatible changes, like if you're adding a new field to an API, protobuf will handle forwards and backwards compatibility for that for you, so you don't need to care about that so much. So we don't change the package name for those. But if you want to make a breaking change to an API or a behaviorally breaking change to an API, we require a new version number to be embedded in the package name, which means it gets a different URL path, which means you have to handle that on both sides.
Anyone else?
Over here.
I'm mostly a backend engineer, so
Yeah.
yes, maybe some stupid question. For the bidirection stream, what's the use case for that?
So I had one example in there in the transaction stream where we're sending down data, we're acknowledging receipt of that data. But it could be, if you're doing a text chat app, you've got messages going back and forth is the easy example. Video streams would be similar, though you wouldn't use gRPC for a video stream, but it's anything that has two-way communications that can happen simultaneously.
But for bank
Yep.
app, right? So do you have what's the use case for do you have a lot of conversation back and forth at the same time?
So it's this one. Let me bring the slide up for it again. This one with the transaction stream, where we get sent a transaction and we acknowledge receipt of that transaction. So that's one message going this way to say, hey, here is transaction number 10. You bought a beer at the pub. And then the app itself will send back a reply to say, yep, we've got transaction number 10, all good. We've saved it, everything's good. So that's a two-way stream because you've got the message coming from the server and you're responding to that server, to that one inside the same connection.
So it's just probably the size is smaller, it's faster than the REST API. Okay.
Yeah, you could do that as if you're in HTTP 1 world, you could do that as multiple HTTP calls going in each direction, but that's a lot of overhead. Every time you make a new HTTP connection, there's potential that it can fail. There's error handling you need to do for that. If you've got a connection that's open, it's stable, and you can just send data back and forth, there's no overhead, no connection, waiting for the connection to happen, all of that sort of stuff.
Okay. Is it required for to use with HTTP 2 or?
Whoops, shouldn't have touched that.
Cursed laptop.
Thanks, Pat. gRPC supports more than just protocol buffers. It does actually have a REST, a JSON compatibility mode, and it does support HTTP 1.1. It doesn't support all of the same functionality over HTTP 1.1 though.
That's it.